So the atoms that are contained within either a polyatomic ion or a molecule are held together via covalent bonds. These covalent bonds form as a result of the atoms sharing electrons. When the atoms share electrons to form a covalent bond, what they're going to do is they're going to continue to share electrons until each atom in our molecule or polyatomic ion has a complete octet. Once an atom obtains a complete octet, it has a stable noble gas electron configuration and doesn't want to change its number of electrons any further, and it will become unreactive and the molecule will be stable. So this was all kind of formalized by an American chemist in the early part of the 20th century, so in the 1900s. His name was Gilbert N. Lewis, and his model described both not only molecular or covalent bonding, but also ionic bonding. And he said the following. He said that valence electrons are those that are important for bonding, and the reason for this is because they're the electrons that are on the outermost surface of the atom, so that when two atoms come together and begin to interact, it's through these outer valence electrons that they're going to experience each other. When atoms interact and form bonds, valence electrons will either be transferred or shared. Transfer of electron, giving rise to ionic bonding, occurs between elements that are quite different from one another, that are a long way apart on the periodic table. In particular, it occurs between metals, which are on the left of the periodic table, and non-metals, which are on the right of the periodic table. When electrons are transferred, ionic bonds are formed as a result of the attraction between the ions that are formed. Now, if two similar elements come together, two similar non-metal elements in particular come together, then electrons will be shared, and this will result in the formation of a covalent bonding. Now, whether electrons are shared or transferred, the net result is that the atoms involved in the sharing or the transferring of electrons will obtain a complete octet of electrons, and then they will become sort of stable and happy, and they will cease to react any further. So just like we used Lewis symbols to illustrate how electrons were transferred in ionic compounds, we can use Lewis structures to show how electrons are shared in molecules, in molecular compounds. So let's think about what happens when a hydrogen atom with its one valence electron interacts with a fluorine atom which has 7 valence electrons. What happens is these unpaired electrons here are shared between the two, and so we end up with a situation like this. Now, this hydrogen atom's nucleus will experience a inwards pull towards that pair of shared of electrons, and so will that fluorine atom. So we have one shared pair of electrons in the middle there. What's the result of that? The result of that is that hydrogen now has a share of 2 electrons, just like helium, and fluorine has a share of 8 electrons. It has a complete octet, just like all of the other noble gases like neon, argon, krypton, xenon, etc. So by sharing electrons, every atom obtains a noble gas configuration. Now, all of the atoms except for hydrogen want to obtain a share of 8 electrons, and hydrogen always wants to obtain a share of 2 electrons. You'll see in the middle here, we have 2 electrons that are being shared, but these other electrons out here that are placed in pairs around the fluorine atom, they're not being shared, they belong exclusively to the fluorine atom. In order to distinguish electrons that are being shared from those that aren't, we will often represent shared electrons in this way with a line, and one line equals 2 shared electrons. Okay, this line here is a bond, right? We call that a bond. It's a chemical bond, a covalent bond. So we know that when fluorine atoms come together, they get stuck in pairs. Fluorine exists in nature as a diatomic molecule. So why is that? Well, fluorine's in group 7A, which means that it has 7 valence electrons. We've illustrated that in the Lewis symbol here for fluorine. So we've got 7 dots around our fluorine. One of them is unpaired. Now, if these two fluorine atoms come together and they share those two that are unpaired and form a single covalent bond, the net result is every fluorine, each of the fluorines here, ends up with a share of 8 electrons, which is a noble gas configuration, right? So what we'll do though is we want to make those shared electrons look a little different from the other electrons, so we're going to replace them with a line. So what we see is that about every fluorine, there are 6 electrons that are not shared, and there is 2 electrons that are shared. It is the 2 electrons that are being shared that help hold these fluorine atoms together, because the nuclei of each of the fluorine atoms will feel an inwards pull towards them. Okay, so we can think of lots of combinations of other atoms that would form molecules in this way in order to obtain a stable octet. Something to keep in mind is when you see these like single atoms in a Lewis symbol of an atom, think of that as like a hand that's reaching out and wants to pair up with another unpaired dot. And these guys on the edge here, they're already paired up, so they are not grasping to find a pair. And when we have 4 sets of pairs around an atom, it's going to have a complete octet. So we can kind of see that here. As I pointed out, only some of the electrons are actually helping hold the atoms together. Those that are being shared are the ones that help hold the atoms together. They're the ones that the nucleus of each atom feels an inwards tug towards. Because these are the electrons that are helping hold the atoms together, we call those guys the bonding electrons. The other atoms that are indicated in blue here, they're located exclusively on one atom. They're not in any way helping hold those 2 atoms together. So for that reason, we refer to them as being non-bonding electrons. Often, non-bonding electrons are referred to as lone pairs because you can see that they come in pairs. They're referred to as lone pairs because they belong to a lone atom. They belong to a single atom. So non-bonding electrons are those that are not being shared. They don't help hold the atoms together. Bonding electrons are those that are being shared, and they help hold the atoms together. Sometimes non-bonding electrons are referred to as lone pairs. So we might say something like this, that this fluorine atom has 3 lone pairs. Right? Because each of these is a lone pair. We can draw Lewis structures for molecules that have more than 2 atoms. Here we're looking at the combination of 2 hydrogen atoms with 1 oxygen atom to form a water molecule. So the hydrogen atoms come from group 1A, so they have 1 valence electron, and the oxygen atom comes from group 6A, so it has 6 valence electrons. You can see these are the guys that are going to pair up, these single dots here. And after the pairing, you see that the oxygen atom has 8 electrons around it, and then each of the hydrogen atoms has 2 electrons around it. Again, to distinguish the bonding from the non-bonding, for every pair of bonding electrons, I'm going to replace that with a line, so we end up with a more familiar diagram for the water molecule. So we can see 2 electrons between each hydrogen and the oxygen atom, and then the oxygen atom has 2 lone pairs on it. The next diagram is showing the formation of an ammonia molecule where we have a total of 4 atoms, 3 hydrogen atoms and 1 nitrogen atom. The nitrogen atom is in group 5A, so you can see that it has 5 dots around it, and 3 of them are looking for partners. So they're going to combine with the 3 hydrogen atoms, which are in group 1A, and when that happens, their unpaired electrons there pair up, and we end up with the nitrogen atom has a share of 8 electrons, and each hydrogen atom has a share of 2 electrons. Now this is kind of quite complicated, so again we're using the lines here to indicate the bonding electrons and differentiate them from the non-bonding electrons or the lone pair. So we would say that this guy's got 1 lone pair, but we would also say that it has 2 non-bonding electrons. There are also in here 2, 4, 6 bonding electrons. Go. Okay, and we can go even bigger. This molecule at the bottom is called methane, and there's 5 atoms involved. The carbon atom in the middle there is in group 4A, and we see that it has 4 valence electrons, and then of course hydrogen atom still in 1A. So we're going to pair up all of our unpaired dots to make sure that every atom has an octet, or in the case of hydrogen it gets a duet, doesn't it? And so now we can see that each hydrogen atom has its duet of 2 electrons, and then the carbon atom right there in the middle has its complete octet. Again, it gets a little bit complex interpreting this diagram. It's hard to see what is being shared and what is a non-bonding electron. So we're going to replace all of the shared electrons with lines where we have 1 line represents 2 shared electrons. Okay, so that's got a little bit of a sort of a lowdown on how we construct these Lewis structures to indicate how electrons are being shared. So just a little bit of a heads up. Remember that the atoms that are going to be doing this type of bonding are your non-metal atoms. And perhaps your metalloids, because metalloids, remember, are kind of, sometimes they behave like metals and sometimes they behave like non-metals. But the important thing to recognize is that the group number for a representative element is equal to the number of valence electrons, hence the number of dots that are in the Lewis symbol of the atom. So group 7A, they've all got 7 dots around them. The other thing to recognize is that the number of unpaired dots is an indicator of the number of bonds that these atoms like to form. So this is an indicator of the most common bonding pattern. So those elements that are in group 7A most commonly form 1 bond. Those elements that are in group 6A most commonly form 2 bonds because they have 2 unpaired dots, and so on. So like I said, this is often referred to as an octet vacancy. So if we look at the noble gases, they have no unpaired dots and they tend not to form bonds. Now the fact that fluorine and also hydrogen, the group 7A, actually just say it's not just fluorine, the 7A elements and hydrogen have 1 unpaired dot, that means that they can never be found, or they are not normally found, not often found in the middle of a molecule. They're always found at the end of the chain of atoms because they've only got 1 hand that can reach out and grab onto another atom because they've only got the 1 dot. So typically hydrogen and the group 7A elements are going to be found at the end of a chain of atoms, right? That's where they're most likely to be found. Now it turns out that you can share more than 2 electrons. When 2 electrons are shared, we get what we call a single bond. And so that's what we saw in the water molecule here, right? There's 2 electrons being shared here. But we can also share 4 electrons. And a good example of this is the O2 molecule. We know when two oxygen atoms come together, they get stuck because oxygen is a diatomic element. So what happens is oxygens are in 6A, so they have 6 valence electrons with 2 unpaired dots here and here. Same on the other one. So what's going to happen, they're going to share all those unpaired dots. And when we do that, we end up with 4 shared electrons. And we put one single line for each pair, for each 2 shared electrons. So we put a double line between the 2 oxygen atoms, and we refer to that as being a double bond. So the same can happen if we can also share more than 2 electrons. We can actually share up to 6 electrons. We don't ever see quadruple bonding. When 6 electrons are shared, we get what we call a triple bond. So nitrogen's in group 5A, and again, we know that nitrogen is one of our diatomic elements. So every atom of nitrogen has 5 valence electrons, and it's got 3 unpaired dots. So when 2 nitrogen atoms come together, they want to share these unpaired electrons, and that gives a total of 6 electrons being shared between the 2 nitrogen atoms. We can represent that with one straight line, one line for each pair of electrons, and that puts 3 lines between the 2 nitrogen atoms, which is why we refer to this as a triple bond. So we can share 2, 4, or 6 electrons, giving rise to what we call single, double, and triple bonds. So if we put in here single, double, triple, there are a few things to keep in mind. They get stronger as we go this way, but they also get shorter because the tug inwards is greater for double and triple bonds. So they get shorter and shorter and shorter as we move from single, double, triples, and they get stronger. Now, the fact that the bond in N2 is a triple and the bond in O2 is only a double has some very real consequences. Nitrogen, which makes up about 78% of our atmosphere, and oxygen, which makes up about 21.5% of our atmosphere, nitrogen is really unreactive. It's very hard to get N2 molecules to react. Generally, you need temperatures of the sort seen when lightning strikes or when there are like forest fires. You need really high temperatures. So it's difficult for organisms to take in the nitrogen that they need in order to build their amino acids, and which are used to make proteins. So that's problematic. Oxygen, on the other hand, we can breathe that in and use it as part of our respiration at normal temperatures. We don't need, we don't have a furnace inside us running at the temperature of a forest fire. We are able to metabolize an oxygen at body temperature of about 36 degrees Celsius, I should say. So keep that, or 37 degrees Celsius. So keep that in mind that, the reactivity of oxygen versus nitrogen is very real. Okay, now if an atom is going to form a multiple bond, that is a double or a triple bond, then it has to have more than 2 octet vacancies. So what that means is that hydrogen, or 2 or more octet vacancies, I should say, hydrogen and the halogens in group 7A, we're not going to see them forming these double bonds, right, and these triple bonds because they just don't have sufficient number of octet vacancies. We already mentioned that we're most commonly going to be seeing hydrogen and the halogens at the end of a chain of atoms and not in the middle position, right? We're going to see them there because they've only got that 1 octet vacancy. That's where we're most likely to see them. Now, I always say tens because as soon as in chemistry you make something an absolute, chemists will try and find an exception to the rule. And there are exceptions to the rules, right? So, but people have very deliberately gone out of the way to to find those things, the overwhelming majority of molecules follow the basic rules that I'm telling you about now. So when we get to group 6A, these guys have 2 octet vacancies. So what that means is there's a couple of different bonding patterns that we're going to see for these kinds of elements. So we're going to see these guys form typically 2 single bonds, leaving them with the 2 lone pairs, or we're going to see them form a single, I shouldn't say a single, one double bond, again, where they have the 2 lone pairs. So when we move to group 5A, and we think about the typical bonding patterns, these guys have 3 unpaired electrons, and they've got 1 set of paired up electrons. So what we typically will see are 3 single bonds with 1 lone pair, a double bond and a single bond with 1 lone pair, or we'll see a single triple bond and 1 lone pair. Now when we move to group 4A, this is the carbon-containing group, what you see is that the elements in this group have 4 octet vacancies. And so this gives a lot of possibility for different patterns of bonding. We could have 4 single bonds with no lone pairs. We can have a double bond and 2 single bonds with no lone pairs. We can have a triple bond and a single bond with no lone pairs. Or we could have 2 double bonds. So these elements are the most versatile as far as their bonding possibilities are concerned. And it's for this reason that is, or this is one of the reasons why we are, or why on our planet we see predominantly, almost exclusively, carbon-based life forms. The majority of the really important compounds that make up living things on our planet use carbon as the basic structural framework because the type of bonding that carbon can participate in is so diverse. So you can build a very wide range of molecules using these group 4A elements. Now, it's interesting that there have been some science fiction writers that have proposed that perhaps you could make some silicon-based life forms. Maybe if you're in a different place in the universe where silicon was more abundant than carbon, then you could substitute silicon in things like proteins and DNA and so forth, and you could imagine silicon-based life forms, which is kind of an interesting concept, isn't it? All right, so this is where it gets a little weird. This gets a little tiny bit weird. In everything that we've considered so far, each atom in the bond contributes the same number of electrons. So we have a hydrogen atom and a fluorine atom coming together, and they each contribute 1 electron. We had 2 fluorine atoms coming together, and they each contributed 1 electron. We had a bromine and a fluorine coming together, and they each contributed 1 electron to the bond. Okay, there you go. So every atom's putting in the same number of electrons. When we did the nitrogen with the nitrogen, we had each atom contributing 3 electrons apiece. The same idea, right? Yes, always an equal number of electrons from each atom. So this isn't always the case, and the examples where it's not always the case are what we call coordinate covalent bonding. And what happens in coordinate covalent bonding is that both of the electrons in a bond come from the same atom. So in a regular covalent bond, like we've been talking about so far, what you'll have is 2 atoms coming together to form a bond, a single bond, and each of them will provide 1 electron. And then we end up with the shared electron pairs. Okay, so we can have up to 2 electrons in an orbital. So what this is really happening here is 2 orbitals, 1 on each atom, each of which is half filled, are overlapping, right? And then that gives a new region of space that contains the shared electron pair. In the coordinate covalent bond, what's going to happen is we have a filled orbital on one atom overlapping with an empty orbital on another atom. And the net result is exactly the same, right? So we don't need to have, in this case, an atom that has a partly filled valence shell, right? Yeah, we don't need that. We're going to give both of the electrons there are going to come from another atom type. Okay, so let's have a look at this, right? So first of all, if we are going to get a coordinate covalent bond, we need to have at least 2 octet vacancies. We've got to be able to accept up to another 2 electrons. So here's an example here. We've got hydrogen connected to oxygen, which is connected to chlorine. There we go. And you think that we would be done there, that this would be stable, every atom has 8 electrons around it, there's nothing more that could go on here. But then now let's look what happens. We're going to bring in another oxygen atom and see what happens. All right, so if we bring in this other oxygen atom, it's got 2 octet vacancies. Basically what's going to happen is we can think of it like this. These 2 electrons are going to end up shared. This guy's going to move down here. And then when we do that, we end up with this structure. And if you go through here, you see that every atom has a noble gas configuration. So that indicates that it's stable. The hydrogen has 2 electrons. This guy's got 2, 4, 6, 8. It's stable. This guy's got 2, 4, 6, 8. And then the atom that we just added, 2, 4, 6, 8. So this is a stable configuration. Now this is called a covalent. This is called a coordinate covalent bond because both of the electrons that ended up being shared by that chlorine and the oxygen atom that came in come from the chlorine atom. Okay, so sometimes we're going to see this type of bonding, but it's fairly rare, and something that can kind of like help us detect that this type of bonding is occurring is we normally see a deviation from the expected bonding pattern. And in this case, hopefully you can see what that deviation is. It's that this chlorine in the middle here, remember that chlorine is in group 7A, we normally expect that chlorine, because it has only the 1 octet vacancy, is at the end of the chain of an atom. It's not normally in the middle of a chain of atoms, and in this case, it's in the middle of a chain of atoms. So that kind of like is often a big hint that we've got something like coordinate covalent bonding occurring. Okay, so there are some systematic procedures for drawing Lewis structures, and I'm going to run through them now. This is a 6-step process, and this kind of guarantees that you always get the correct Lewis structure for your covalent compound or your polyatomic ion. So the first step in this process is to count up the total number of valence electrons that you have available to share in your molecule. And now how we know the valence electrons that a particular atom has is to look at the group number in the periodic table. So that's what we're doing there. And then we also have to take into account how many atoms of each particular type there are. So in this molecule here, carbon Cl4, for the carbon atom, it's in group 4A. So that means that it's got 4 valence electrons. The chlorine atom is in group 7A, so that means that it has 7 valence electrons. But what's important is that we recognize that there are 4 chlorine atoms, so we've got to times that by 4. So now we have to add everything together. So 4 electrons from the carbon plus 4 times 7 electrons for the chlorines. 4 plus 28 gives me 32 electrons. And so these 32 electrons I have to organize in such a way so that all of the 5 atoms that are in this molecule have an octet. The next thing that I need to figure out is the arrangement of the atoms. What atom is going to go in the middle, and then what atoms are going to go around the edges. So there are a few things that are going to help you with this. Hydrogen is always on the outside because it can only form that one bond. Then the next step is that the element with the lowest group number, that will be the central atom because that's the one that's going to need to make the most bonds to get an octet. It's going to have the greatest number of unpaired dots. Now, occasionally you'll get a molecule or a polyatomic ion where the elements involved are in the same group, and a good example of this is the compounds between sulfur and oxygen. And if that is the case, then we always go with the one that is lower down in the group, that is the one that has the higher period number, as being the central atom. Now, once you've got all of the central atom, all of the others are going to be what we call outer atoms. So the second step after you've counted up your valence electrons is to determine the arrangement of atoms. In our case, we've got carbon Cl4, CCl4. So carbon is in group 4A, chlorine is in group 7A. Carbon has the lower group number, so it's going to go in the middle. Chlorine has the higher group number, it's going to go on the outside. So the general layout of things is going to be like this: carbon in the middle with the chlorines on the outside. Now, I should point out that we're only ever going to be looking at atoms that have one central atom with then a bunch of other atoms, and they may not all be the same, on the outside. We're never going to be looking at situations, or I'm never going to be asking you to draw molecules where the atoms are perhaps connected in a closed shape, nor am I going to be asking you to deal with situations where we have very long chains of atoms and there are what we call multiple central atoms, like in this case here, where we've got 2 atoms that are in the middle of that chain. In our cases, we're only ever going to be having one atom in the middle of the chain and then a bunch of atoms on the outside. Okay, so that's the general layout of things. Now, the next thing is kind of pretty obvious. In step 3, we recognize that the outer atoms have to be connected to the central atom by, at the very least, a single bond. So the third step is to make sure that every outer atom is connected to the single atom by a single bond, because that's got to be the case, otherwise these guys aren't connected at all. So every line that we draw to the central atom represents 2 electrons, and we need to subtract that number of electrons that we use to get the basic structure from our total. So in this case, we started with 32 from step 1, and then we added, for each of the 4 atoms, we draw in a single bond, which uses up 2 electrons. So 32 minus 8 leaves me with 24 electrons left to work with. Okay, so at this point, what I'm going to do is I'm going to start adding these 24 electrons until I run out. And how I'm going to add them is as lone pairs to the other atoms, but I'm going to work from the outside in. So my next step is to complete the octet of all of the outer atoms by adding lone pairs. And all of the lone pairs that I add, I'm going to subtract those electrons from my leftover 24 electrons. So I'm kind of keeping a tally, right? So I start off with 32, and then I used 8 of them, so that's 24, and now I'm going to add lone pairs. Now, previously we had carbon with chlorine, 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 chlorine. So every chlorine at this point only had a share of 2 electrons. So I've got to put another 6 on every chlorine to get it up to 8. And I've got to do that for all 4 of the chlorines. 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. So I need to subtract from my 24 4 lots of 6, and that means I've got no electrons left. Okay, so I've placed all of my electrons. Now, at this point in time, once my count gets down to 0, I can't add any more dots or lines to the page. I don't have any more electrons. All I can do is move around the electrons that are already there. So my next step is, if I have any left over, which I don't in this case, would be to put those on the middle atom, right? So the 5th step is, if you've got any leftover electrons, put them on the middle, right? So there aren't any in this case, and that is often the case. But if I did put some on the middle, I'd have to subtract that from the total. And then the very final step is to check, once I've got down to 0 electrons, so I went 32 minus 8, and then I did another 24, gave me 0 electrons. Once I get down to 0 electrons, everything has been placed. I have to check my central atom and see if it's got an octet. If it doesn't have an octet, what I'm going to do is I'm going to bring in some of my non-bonding electrons and make them bonding electrons. And then what I'm going to do is by doing that, I'll make double or even triple bonds if need be. So I don't ever think about making a double or a triple bond until this electron count has got down to 0. So it's always the very last thing I do. Now in this case, when I check my carbon atom, 2, 4, 6, 8, it already has a complete octet. So I don't need to do this step of converting some of my non-bonding electrons into bonding electrons. So we're going to do one now where we do need to do step number 6. So you can see how these double bonds form. I'm going to draw this out by hand. So step 1 is count up your valence electrons. So carbon's in group 4A. So there's 4 valence electrons for the carbon. And then we've got 2 times oxygen. And oxygens are in group 6A. So that means we got 2 times 6 for these guys. There they are there. So 4 plus 12, 16 electrons to work with. Now, our 2 rules for deciding what atom goes in the middle is the one with the lowest group number goes in the middle, which in this case is carbon. So carbon goes in the middle and oxygen is the 2 oxygens are on the outside. So we know that the pattern in which these guys are going to be connected is like this. Carbon in the middle, 2 oxygens on the outside. Now, the oxygens need to be connected to the carbon by at least a single bond, and drawing in each of those single bonds uses up 4 electrons from our total of 16. So once we get to this point, we've got 12 left to place. So what do we do now? Every carbon here, every oxygen here, has 2 electrons about it at the moment. So on each of the oxygens, we have to place another 6 electrons to complete their octet, because this step requires that we complete, step 4 requires that we complete the octet of the outer atoms. So 2 times 6 is 12. After forming our bonds, we had 12 electrons left. So that's there, and then we've got to subtract away what we used to complete the octets of the oxygen atoms. So that leaves us with 0 electrons left to place. So at this point, we don't need to do step 5. Step 5 was if you had any leftover electrons, we would have put those on the carbon, but we haven't got any to put on the carbon. So now we're up to step 6. So we're going to begin with this. What we have to do is check if our central carbon has an octet. The central carbon at the moment has 2, 4 electrons around it. So that means I've got to bring in 4 non-bonding electrons and turn them into bonding electrons. So I'm going to bring in those guys there, and you turn them into bonding electrons. And then I'm going to bring in these guys here and turn them into non-bonding and turn them into bonding electrons. So we've got to erase that, yeah, and erase that there. And there is our final Lewis structure. Every atom has an octet, and we use the total of 16 electrons. And you can count that up: 2, 4, 6, 8, 10, 12, 14, 16. And if you check every atom, you'll see that it has an octet. So once you start doing this for a while, you get quicker and quicker and quicker of drawing correct Lewis structures. So typically what we'll see are a few patterns. When a group 7A element or a halogen is on the outside, it forms 1 bond. Oxygen atoms most commonly form 2 bonds and 2 lone pairs. Nitrogen atoms most commonly form 3 bonds and 1 lone pair. And carbon atoms most commonly form 4 bonds and 0 lone pairs. Now these are not hard and fast rules, they're kind of general trends. You'll see exceptions to them all the time. Okay, so that brings us to the end of this section on molecular compounds. There is just one comment that I want to make, which is regarding polyatomic ions and their Lewis structures. So I'm going to illustrate that with this example here, and all it requires is that we slightly modify our procedure in step 1. So step 1 in drawing a Lewis structure of a covalent species is to add up valence electrons. So if I'm drawing the Lewis structure for the polyatomic ion NH4+, I have to recognize that the reason that it has the plus is because it has lost 1 electron. So how many valence electrons do I have? Well, nitrogen is in group 5A and oxygen is in group 1A, and then it's got the +1, which is the charge, and I have to account for all of those things. So I get 5 electrons for the nitrogen, and then I get 4 electrons, 4 times 1 electron for the hydrogens, and then finally, because it's got a +1 charge, I have to take away 1 electron because the +1 charge tells me that I lost 1 electron. So I put all of that together, and that ends up with there being a total of 8 valence electrons. So for polyatomic ions, you have to slightly modify that first step to take into account the charge. We're going to do another, and then everything else is the same. We'll do another one with a polyatomic anion, and remember the polyatomic anions are far more common than polyatomic cations. So for a polyatomic anion, a good example would be SO4 2-. Sulfur is in group 6A. Oxygen is also in group 6A, and the 2- charge there tells us that we didn't lose. Sorry, that we gained 2 electrons. That the neutral species gained 2 electrons. So I get 6 electrons for the sulfur because there's 1 of them, and then I've got 4 times 6 electrons for the oxygens, and then I have to add in 2 electrons for the double negative charge. So 5 times 6 would be 30 plus 2, that would give me a total of 32 electrons. So the only thing to be aware of when we're drawing Lewis structures for polyatomic ions is add in electrons equal to the negative charge and subtract electrons equal to the positive charge. Okay, we have one tiny little section left on this video. It's really only going to be, I think, 1 slide. So we'll talk about that now. So our last section is we have to talk about the differences between covalent compounds in comparison to ionic compounds. So covalent compounds have a really wide range of melting points. They can be either solids, liquids, or gases. So water is a liquid at room temperature, and then something like iodine is a solid at room temperature, and then something like carbon dioxide is a gas at room temperature. So kind of all over the place. If these compounds are solids, they tend to have melting points that are lower than is typical for ionic compounds. So low melting point solids and liquids or gases are typical physical states for covalent compounds at room temperature. Typically, covalent compounds will be poor conductors of electricity and heat. You don't see electrical cabling in your house made out of plastic. Those things are made out of metals. You don't see, pots and pans made out of plastics. They tend to not be great conductors of either electricity or heat. Now, there are exceptions to that, of course. And in general, covalent compounds have worse solubility in water compared to ionic compounds. So we always talk about salt water, and if you remember, salt is another name for an ionic compound. Salt water is water that contains a large number of ionic compounds. Again, there are exceptions to this rule, but this is kind of the general trend. Okay, hope that was helpful. That brings this section to an end. Like I said, it was just the one slide. So yeah, I hope you found the video useful. It's quite a long one. I go into a little bit more detail than what you'll see in the book, but I think it's helpful and it'll be really useful when it comes to solving your homework problems. Okay, good luck with everything. Bye.